this R0, which is going to tell us how fast this is actually decaying. Shortly thereafter, he proposed a different form where he says that, okay, actually we're going to need a couple of different force constants, one for nearest neighbors along the chain. So anything that are close together, they're going to you're going to have one force constant, and then if you're farther away than just nearest neighbors, then a decay with a sixth power sort of decay. And then more recently, Yang and Jernigan proposed another force constant where you say that this dies off as 1 over r squared. So which one is best is really a matter of choice. And this is something that can be encoded into Prodi. So if you know a little bit of Python, you can come up with your own customized force constant functions to suit your needs. Now, why would you want something like that? We did a study a couple of years ago looking actually at what kind of force constants are going to be best, what form of the function is actually going to work. And what you can see here is examples for 3 different proteins where we've taken the NMR structures from the PDB of those proteins, and we have looked at what the ENM calculations are going to be for the mobilities versus what is being shown by the NMR structures, assuming that the differences in models is actually showing us the dynamic range of the molecules. And what we can see is the black line. I'll look at this middle one. The black line shows what we find from the NMR structures, right? And we can see that there's this large peak, for example, right here, where there's a lot of mobility. And the red line is showing what we would get just by using some cutoff and a uniform force constant. And we can see that we don't get quite the same peak at this area, and we get a larger peak at this area. Now we can modify, and this we did empirically, and come up with a customized force constant where we've looked at the distance dependence, we've looked at what are the neighbors along the chain. We've assigned different force constants if you're nearest neighbors along the chain, if you're second neighbors, and so on. And where we've looked at some hydrogen bonding just to get a guess of which atoms are going to be, or which residues are going to be hydrogen bonded. We included that into the function. And what we can find is that we get this blue line, which has, in this case, just a slightly better agreement. In the top case, no better agreement. But for this particular case, you can see that the blue line actually picks out these flexible regions that weren't picked out just by using a uniform force constant function. So this is just a simple example of where customization that is allowed in Prodi might be useful in studying elastic network models.
Is this even structure dependent? Like, or is some structure maybe with this applying the right force constant?
So in this case, it's entirely the same, the question was, is this structure dependent? And in this case, what we have used is the same model. The blue one, it is the same model in all 3 cases. And we did this for several proteins. So it's structure dependent only insofar as the force constant function itself is not structure dependent, but it takes into account structural information. So it takes into account things like chemical distance. The same form in all cases. Okay, this is actually gamma structure based. Amit implemented this in Prodi, so this exact form of the function is actually in Prodi, but customizing your own functions you can find in the ENM tutorial under custom gamma functions, which Amit will explain at some point. Something else that has been mentioned is the influence of crystal contacts. So in this case, what we have is for this protein, we can look at what are the B factors taken from the X-ray structure. So how much are the residues moving? And we can say that that is a surrogate for the motion of the protein. And that we get as this line. Okay, we can look at what we think is the experimental mobility as a black line with residue number. Now, if we use an elastic network model, what we find is that we get this large peak right here around residue 91, 92. That's commonly known as a tip effect. This happens actually in elastic network models, and the reason for it is just simply that those residues are not constrained by the by the model itself. There are very few constraints over here. So to get rid of that, of course, we can say, well, let's consider the entire crystal lattice that this is inserted in, and then we can see that there's going to be some contact there, and maybe that's going to damp things down. So that can be done, and that can be done actually by reducing the model, again using Prodi. What we find is that if we look at just the internal motions of the molecule by itself, then we're going to get this red line. If we use the crystal context, we get the green line, which actually gives us a little bit more motion in this region. It reduces the motion a little bit there. That's not quite the whole story. We can do a little bit more and actually include the lattice vibrations, that is rigid motions, and that gives us a better match together. So these are the type of study that you might need to have some customized functions for. Yes?
So could you also use the diffraction data?
Which diffraction data?
Of which PDB if it's an X-ray?
Yes, so the diffraction data is actually we're using the B factors. That's what's shown actually in the black lines.
The whole ensemble?
The B factor is for each atom in the protein. So we can take the B factor for the alpha carbons.
Over the complete diffraction set?
Yes, the B factor is showing the motion over the entire crystal. But including the crystal context can be done just by building the lattice and then reducing the model to see what kind of motions you would get, let's say, in the presence of a crystal. Okay, moving along. So another question is, what about the influence of the environment on the proteins themselves? So this is actually relevant in the case of membrane proteins. So shown here is a bacterial homologue of the glutamate transporter, where first there was a crystal structure for an outward-facing conformation that was solved several years ago. I don't remember the exact date, sorry. It looks like sort of a bowl shape. This is a trimer. It's a homotrimer. And you can see that there's this dip in the middle when you look at the side. And it's inserted into the membrane so that these transport domains, which are shown in blue in this structure, are facing the outside of the membrane. Okay? And then if we look at the inward-facing structure, which was published, I believe, in 2009, then what we see is that these transport domains, shown in blue here, actually move through the membrane. And this is a large motion. You can see the membrane is about 30 angstroms thick. And there's a large-scale motion of these transport domains through the membrane. And how might that type of motion come about? And in fact, I can tell you that since what I'm going to show you, we have done simulations ranging for several microseconds. Is that? Microseconds. And we haven't seen this type of motion. So these are long time scale motions. Okay, this is just a cartoon that was actually created when the inward-facing structure was solved, just to show what that motion is actually going to look like. So we can see that there's one domain that is stuck inside the membrane, there's another one that's moving through. And looking at this, we can say, okay, the reason for that is just because you have a membrane that is surrounding the protein that is preventing some kind of motion laterally, or that's preventing any radial motion. So we did something very simple. We took the Hessian, which has this form. This is just for one element of the Hessian, one 3x3 element of the Hessian. And we said that in all cases, you have this gamma term, which is the spring constant. And instead of leaving it on the outside, we inserted that inside. And we said that, let's say that the gamma term can be different in the three different directions, in x, y, and z directions. And we make the z direction softer than the x and y directions to say that there are constraints for motion that is against the membrane, that is opposing the membrane. And what we find is the following. So if we just use a basic elastic network model, we get this opening and closing motion, okay, which doesn't show really this up and down transport of that we actually see through the crystal structures of this protein. Okay? If, on the other hand, we modify the force constants so that we make motion in the z direction easier than that against the membrane, we see that it's not as much opening and closing, and that in fact we do get a lot of up and down motion that might explain how we're actually getting transport going through the membrane. So this was just a very simple modification to the structure of the force constant. Again, this can be encoded simply. It's about 3 lines of code, and yet we get a lot of difference. But then the question is, yes?
I was going to ask, were these generated based on the outward-facing structure, the inward-facing one?
This is for, so okay, in this case what I'm showing you is starting with the outward-facing structure and looking at the modes. I'll show you results actually, not movies, but results from the inward-facing structure, and in fact it works both ways. So an alternative model is just to say, what if we wanted to explicitly consider the membrane? Because what we did in the previous one is we said we have this membrane that is surrounding the protein, and that's making some kind of a constraint on the motion, on this opening and closing motion. So what we've done is we artificially said that we're going to make motion easier in this direction across the membrane. But we didn't actually look at what the membrane does. So there is a way to actually put in the membrane and look at what are the effects. So what I'm showing here is, again, this outward-facing conformation with an artificial membrane placed around it. In this case, it's just some beads, which will be nodes in the elastic network model. They're placed at distances that put them roughly the same distance as the residues inside the protein are from each other. And I just put them in a regular lattice, just to simulate something that is constraining the motion of the protein. And then we can calculate the modes for this entire system of protein and a bit of the membrane. Okay? The problem is that if we calculate those modes, let's say that there are 1,000 residues in the protein and we have 1,000 little spheres representing the membrane, we're going to have 2,000 nodes in our network, which means we'll have 6,000 modes in the network. And the part that is attributed to the protein is really only going to be half of that. So we have more modes than we have that are possible for the protein itself. So there's a way around this. And the way around it is actually described in these papers at the bottom by Ming and Wall and by Zheng and Brooks in 2005. And what they say is this: we take the Hessian, this is the full Hessian for the full system, and we divide it into 2 different parts. One is for the system, which will be the protein, and this is going to be the top corner. And then we say that the environment is down here. So if we can imagine that the Hessian actually corresponds to some long vector of residue coordinates or of node coordinates, then that vector will be separated into a system and an environment component. And then of course we have these interactions that are between the system and the environment. These are cross terms. You have a question?
Yeah, how are the beads of the membrane connected to the residues of the protein?
So the beads of the membrane, yes. How are the beads of the membrane connected to the residues of the protein? In this case, all that we have done is very simply, we just used a cutoff distance and a uniform force constant. So what we have said is that the beads are essentially the same. They behave the same way as the residues in the protein. But what we can do is we can say that if we want to get rid of the effects of the beads, we can essentially integrate out all those degrees of freedom. Okay, and what that'll give us is an effective potential for the system itself. Here system is shown in S, and that effective potential is actually going to be, again, harmonic with some Hessian, which is H prime. Now H prime can be calculated by looking at this HEE, taking its inverse, multiplying it by these cross terms, and subtracting it from our original Hessian. All of this is done in reduced model, in Prodi. So if you actually have a model like this, all that you have to do is specify what is the system that you're interested in, what is the environment, and Prodi will calculate this effective Hessian, and then we can get some modes that we can look at. In this case, here are some results. So what I'm showing here is if we look at the deformation vector between the inward and outward facing conformations, and then we look at how that deformation vector is accounted for using modes of different models. What we can see is if we just use A and M with a 15 angstrom cutoff, then we get this black line that shows that, in fact, a lot of the deformation is accounted for with the first 30 or so A and M modes. This is starting from the outward-facing conformation, going to the inward-facing conformation. On the bottom, it's starting from the inward-facing conformation and going to the outward-facing conformation. The deformation vector is the same, The modes will be different because those modes are calculated based on the inward-facing conformation. And again, we can see that about 30 modes are required to get something like 80% of that deformation vector. If we use what's shown in pink, if we use this first method where we've just altered the Hessian just by adding some term, making it weaker in the z direction, what we see is that instead of this gradual increase, we get a single jump with one mode that accounts for about half of that deformation from the inward or from the outward facing conformation. So in that case, what we see is that we get some motion that actually agrees very well with this large scale deformation. And then we can see what's shown actually in the blue is the method where we explicitly include the membrane in little spheres and then integrate that out. And we can see again that using just very few modes, we get a large jump, and then with just a couple more modes, we can account for about half of that deformation, at least from the outward-facing conformation, not so much from the inward-facing conformation for technical reasons. But the point is here that we can make these modifications using a few simple commands, and we can explore different things than, we can extend the utility of elastic network models. And one just final example is coming from the nuclear pore complex. Okay, this is actually an enormous complex, and this is going to show, I hope, that we can extend these things beyond just proteins. So the nuclear pore complex actually sits inside the nuclear envelope. The nuclear envelope is a membrane that bends around, and the pore complex consists of hundreds of proteins that are in some very large complex. A structure of this was solved or predicted actually by Frank Elber and Andre Sali. And they were nice enough to give us the structure. And what we did is put this together and said, okay, this is roughly what the nuclear pore complex looks like. Each node here is actually representing a protein in the complex, a complete protein. Okay, and there are 456 proteins. And of 36 different types. So we took this complex, this structure, we added again the nuclear envelope using just some artificial representation of beads just to simulate this. In this case it was about 2,000 different beads. And then we came up with different cutoff distances between proteins or between the beads that we're using in the nuclear envelope. And we also came up with different force constants for use in the nuclear envelope versus the protein, to say that the protein is more flexible than the nuclear envelope itself, and looked at what kind of modes we get. And again, we integrated out the motion of the nuclear envelope, and what we find are the first two modes are shown here, two views of each. Okay, there are these, not surprisingly, opening and closing types of motions. What's a little bit what we didn't notice, or what we didn't expect necessarily, is that the effect of the nuclear envelope is to decrease the motion of the residues at the center part of the pore complex. That is, if we call this, if this is the z direction, if the axis of the pore is in the z direction, then what we're showing is the mobility as a function of z position. So we can see that anything that is on the bottom or inside the nucleus and anything that is on the top or outside the nucleus is moving more than those things that are in the middle. And this is actually an effect that is due mostly to restraints from the nuclear envelope. Okay, so these are examples of some uses of these elastic network models that are specially refined for special purposes. There are more that I didn't talk about. For example, you can look at pooling. There are a lot of studies that are done using AFM, atomic force microscopy, to pull apart residues. Okay, so we can actually look at how proteins are getting pulled apart using elastic network models. We can look at transitions between states. This, I think, somebody asked about. Actually modeling the pathways. So this is an important aspect of elastic network models, is that we can start off at two endpoints, and we can work along the softest modes, the most available modes, towards the other endpoints. and get at least a guess at what the transition pathway might be. And then that can be explored in more detail using fully atomic MD simulations. And then this is actually shown at the bottom. There have been methods developed for combining normal mode analysis and elastic network models with molecular dynamics so that you can make a large step using an elastic network model, and then you can refine using molecular dynamics and continue to move in that way. And these things I spoke of, but ensemble analysis, a very important application that I'm sure Amit will talk about. So with that, actually, I'll hand it over to Amit so we can get our hands dirty and start actually doing something.